Welcome to Lesson 9 of Module 5, Examples of Functions from Geometry. In this lesson, we are going to use functions to talk about area and volume of figures, and we'll kind of review what we know about volume, which will lead into the next couple of lessons, lesson 10 and 11, at the end of this module. And so some of this will be review and some of it may be new. So we're going to open with an activity. If you find this in your notes, this is going to be the table where we record the information from exercises 1 through 4 so we can look at it all at once. Okay, so here's exercise 1. Use the figure below to answer parts A through F. Okay, so I would like you to work on this independently. You can work on all 4 of the exercises. Just remember to go back to the table to record your results. Okay, so let's continue with exercise 1. So hopefully you've tried these on your own. You'll get a lot more out of this discussion if you have. Okay, what is the length of one side of the smaller inner square? So the length of the smaller inner square is, let's get a color you can see, is 6 inches. And we can tell that from the diagram. Okay, part B asks, what is the area of the smaller inner square? So the area of that smaller inner square, area, we'll let A stand for area, is equal to 6 inches times 6 inches. Remember, area is length times width, or base times height. So this is 6 times 6 is 36. Inches times inches is inches squared. Okay, so the area of the smaller inner square is 36 inches squared. What is the length of one side of the larger outer square? Okay, so we can see from our diagram that that is 6 inches, but I've got an inch here and an inch here. So 1, 6, and 1. So the length of one side of the large outer square would be 8 inches. And the area of the large outer square would be 8 inches times 8 inches, or 64 inches squared, square inches. Use your answers in part B and D to determine the area of the 1-inch white border of the figure. Okay, so we want to know, what is the area of this whole border area? And we're going to use, it says to use our results from B and D to do that. So hopefully you saw that if you took the area of the large outer square, which includes the border, 64 square inches, and subtract off the area inside, 36 square inches, that you would get the area of the 1-inch border. So the area of this border is 28 inches squared. Okay, explain your strategy for finding the area of the white border. So what I did, and you may have had a different strategy, and that is totally fine, but what I did was I subtracted the inside area from the whole area, the area of the whole piece altogether. Okay, so we can complete exercise 2 in the exact same way that we did exercise 1, but it has different dimensions. So the length of one side of the smaller inner square is now 9 inches. So the area of the smaller inner square will be 81 inches squared. The length of one side of the large outer square is still 9, 1, and 1. So it's going to be 11 inches. And so the area of the large outer square would be 11 inches times 11 inches, which is 121 square inches. And then to use my answers, I can still subtract 121 inches squared minus 81 inches squared. And I get the area of the border. Take the whole thing, subtract off the inside, and I get the area of the border. Okay, so you should have an explanation for your strategy, and especially if your strategy is different than the one that I'm describing. Okay, so let's do one more. Actually, before we do that, let's go back and record our answers on the table in the front. Okay, this table could have a little bit better design, but basically we're doing the inside dimension and the area, the outside dimension or side length, which was 8, and that area, 64. And the expression that describes the area of the border would be this expression, 64 minus 36. Okay, and then for exercise 2, our dimensions were 9 and 11. So that gave us areas of 81 and 121. And our expression is 121 minus 81 for the area. Okay, so let's go back to exercise 3 and use those numbers. So the length of one side of the smaller inner square is 13 inches. The area of the smaller inner square is 13 inches times 13 inches, which is 169 square inches. The length of one side of the larger outer square, again, is 13. These are still 1 and 1. That hasn't changed, right? So the length of one side of the larger outer square is 15. And let's keep going. So the area is of the... Did I put inches on that? Inches. The area of this one is 15 inches times 15 inches, which is equal to 225 square inches. And then we can use our answers again. We're going to have 225 inches squared minus 169 inches squared, subtracting off the inside dimension, and that is 56 inches squared. Explain your strategy for finding the area of the white border. Once again, it's to find the areas of the two squares and subtract them to find the difference, to find the frame. All right, so let's go back to our table. And we had 13 and 15. So this is 169 and 225. And we found, once again, we found the difference. Okay, so this is all leading up to this. We've been writing numeric expressions, And now what we want to do is imagine that we want to put this into a computer program where somebody would just have to input the side length of the inner square, and it would tell them the area of the border. So we want to have it work for, we want to use our pattern for any size inner square with a 1-inch border. Okay, so we can write an expression that represents the side length of the smaller inner square. Okay, so here you could have some different ideas for what you'd write for this. It's an unknown, right? We don't know. It's going to be a variable because we're going to let people decide how big they want that to be. So we could use a variable such as x, or we could do s for side length. Either of those would work. So we'll just decide on one. I'm going to use s. So my expression is s will represent the side length of the inner square. Write an expression that represents the area of the small inner square. So if S will represent the side length of the inner square, the expression that represents the area would be S times S. So we could also write that as S squared. Okay, so we just take that, and let's go ahead and label our diagram right here. That length is S now. Okay, so write an expression that represents the side lengths of the larger outer square. So let's look at that. So we've got, once again, this dimension is S, this is 1, and this is 1. So the expression that represents the side length of the larger outer square would be S plus 2, as we've got 2 inches on the sides and S in the middle. Okay, so now we can use that expression and answer part D. So part D says write an expression that represents the area of the larger outer square. So area is the side length times the side length. So it's S plus 2 times S plus 2. And a shorter way to write that would be S plus 2 squared. I need the parentheses because I'm going to add the 2 to the S first, and then I'm going to square it. So S plus 2 squared, it's got to have the parentheses or it's wrong. It's not saying what I mean for it to say if it doesn't have the parentheses. Okay, use your expressions in part B and D to write a function for the area A of the 1-inch white border for any sized square picture measured in inches. So A is the area of the 1-inch white border, and I'm going to use the same method I used before, which is to take the larger square, the area of the larger square, the whole thing, and subtract off the inside, which is S squared. And that gives me a function for the area. So I can say that area of the border is a function of the side length of the inside square. So area is a function of side length. And you could ask yourself, is this linear? And the answer would be no, right? Because of the exponents on the S. The S variable has exponents of 2 on it, and so it's nonlinear. So going back to our first page, we can record for exercise 4, which is just the general formulas. So the side length is S, the outer side length is S plus 2. So here are the areas, S plus 2 squared, S squared, and S plus 2 squared minus S squared is the expression that describes the area of the border. Okay, so we can see here if S is 6, S plus 2 is 8. If S is 9, it's 11, 13, 15. So what we see here is that we can use a function to represent area, a particular area, and we can use, and it can be variables. So that makes it real flexible and usable in lots of situations. So think about, let's look at one of the pictures. Think about what this could be. You know, what in real life, what could this diagram be representing? Okay, so in one of the exercises, they actually called it a picture. So that would be an obvious thing where this inner square is the picture and the outer square is the frame, the border of the frame. Okay, but what about a garden? Could the inner square be a garden plot, and this could be the frame around the garden, or the rock border or something, so that you would want to know the area of. What are some other things it could be? It could be maybe a playground, and these are sidewalks. Okay, it'd probably be feet or yards or some other dimension at that point. But you can see how this function could be used for a lot of different applications. Okay, so we're going to switch gears right now and start talking about volume. So we've talked a lot about volume in 8th grade science. And so volume is just defined as the space that a three-dimensional figure occupies. A lot of times we think of volume as the amount of liquid or a substance that an object can hold, like the volume of a drinking glass is 16 ounces or whatever. But it's a three-dimensional space. That's what volume is, how much space something takes up. And depending on the figure, we have different ways of measuring it. So over this lesson and the next two, we're going to start talking about volume, and specifically functions that describe the volume of different figures. So let's look at this visual here. So if I have some liquid that's filling this figure here, and I pour it into this rectangular prism here, and this is a special rectangular prism because the dimensions of the bottom are 1 by 1. So let's go ahead and give this a unit. So this is 1 foot by 1 foot, for instance. And I've taken all the liquid out of this container here, which has a different type of shape. This isn't a prism, right? Poured it in here, and it fills this up to a height of V. And so I could say that the volume of the solid container here, no, it's not solid, it's obviously hollow. The volume is equal to V. Why would the volume be equal to V, the height of the liquid? Okay, so the reason for that would be that the area of the base of this figure is 1 by 1, or 1 square foot. So I have 1 square foot on the base. So whatever the height is going to be the height times 1 feet squared. That's going to give me the volume. Area of the base times the height is going to give me the volume. So if this height here was, and it won't be to 2 dimensions, say that height, let me get a color here, the height is 7.4 feet. Then the volume would be 7.4 feet times 1 square foot. And so the volume would be 7.4 feet times feet squared is cubic feet, or feet cubed. So that height would be that. So that's kind of how we can think about it. And it wouldn't matter what the unit is. We could change this unit to centimeters or inches or yards or miles or whatever. But just having this unit dimension on the base is going to give me the height of that being its volume. Okay, so that's just one way to think of it about it. So there's some things that we want to remember for volume, and they are that it's always going to be a positive number. It could be 0, but it's greater than or equal to 0. The volume of a unit cube, so the volume of a unit cube, which is a rectangular prism with all sides with a length of 1. So we could think of that as, and we messed around with centimeter unit cubes quite a bit, but it could be any dimension. If I use an inch, it's 1 inch by 1 inch by 1 inch. So the unit cube, the volume of the unit cube is 1 cubic unit. So this one is 1 inch squared. If 2 solids are identical, then their volumes are equal. So that kind of makes sense. And then this is important. If 2 solids have at most their boundaries in common, then their total volume can be calculated by adding the individual volumes together. So sometimes you might have a shape that has something else coming off the side of it, and you can just add the volumes together. We do that a lot with area as well. Okay, so let's look at some examples of calculating volume. So this is in your classwork. So we have, and I want to say up front, you can use calculators on these. I don't expect you to be multiplying these numbers by hand and dividing as well. So calculators are okay on this assignment. Okay, so the volume of the prism shown below is 61.6 inches cubed. And so I would just go ahead and write that piece of information here. Volume equals 61.6 cubic inches. What is the height of the prism? So pause the video and see if you remember how to do a problem like that. How can we find the height of this prism? Okay, so if we know that the volume of the prism is going to be the length times the width times the height, and we're going to call it h, solve for h. So as I simplify this equation, I'm going to take the units out of it so that I just have the numbers. So 8 times 2.2 is 17.6 times h. And then to solve for h, I want to get h by itself, so I'm going to divide by that. And then I'll be able to see that the height is the volume divided by 17.6. What I didn't do yet, and what I'm going to do right now, is to go ahead and substitute in our value for the volume, because we know what that is. So we know that the volume is 61.6 cubic inches. So 61.6 divided by 17.6 is equal to 3.5. And that is our height. So the height of the prism is 3.5 inches. Okay. All right, so let's look at another one. So here we have two prisms, and we're asked find the value of the ratio that compares the volume of the larger prism to the smaller prism. Okay, so I would start by finding the volume. So if this is, we'll call this prism 1 and this prism 2. So volume 1 is the length times the width times the height. I've got 7 centimeters times 9 centimeters times 5 centimeters. So volume 1 is 7 times 45, which would be 315. And the units would be centimeters times centimeters times centimeters, which is centimeters cubed. So volume 2 would be 2 centimeters times 4.5 times 3. So that volume is equal to 9 times 3, which is 27 centimeters cubed. Okay, so we found the volumes, but we're asked to find the value of the ratio that compares the volume of the larger prism to the smaller prism. So when we find the ratio of the volume of the larger prism to the volume of the smaller prism, we're going to write it like this: 315 cubic centimeters compared to 27 cubic centimeters. So that's the ratio of the larger to the smaller. It's going to tell us how many times bigger the big one is from the small one. And that ratio, I can see these both have a factor of 9 in them. And so I get 35 to 3. Notice that the units drop out in the ratio. So the ratio is unitless. It's 35 to 3. So for every 3 cubic centimeters on the small figure, for every 3 here, there are 35 here. So it's 35 to 3. We could write that as a decimal, but we don't really need to. We're asked to write it as a ratio, so we can leave it like this. If you did write it as a decimal, it's not wrong, but this is a useful way of thinking about this ratio. All right, so for exercises 7 through 10, you are going to be recording information in this table, and we're going to just discover some things about volume, see some patterns. Okay, so we want to record the area of the base, the height, and then the total volume. So base refers to the bottom of the prism. So we're going to define that as the side that it's sitting on. So this is the base of this prism right here, the side that it's sitting on. Okay, so exercise 7 says what is the area of the base for this figure over here at the right. So the area of the base for this figure is 12 centimeters. I'm going to write it like this. Area of the base equals 12 centimeters times 3 centimeters. So that's 36 square centimeters. So this is 36 centimeters squared. Okay, so the height, what is the height of this figure? It's labeled right here. The height is 3 centimeters. And what is the volume of the figure? Okay, so the volume is 3 times 12 times 3. 3 times 36, which is 108 cubic centimeters. 9 times 12. Okay, so that's exercise 7. So go ahead and do 8, 9, and 10 exactly the same way. 8, 9, and 10, and then we'll summarize all what we're learning together. Okay, so go ahead and work on those. Okay, here are some results for the remaining 3 exercises. So for 8, what is the area of the base? Well, again, it's 12 times 3, or 36 cubics, or not cubic, but square centimeters. The height of the figure is 8, right here. And the volume of the figure is 12 times 3 times 8, or 288. All right, we'll just check them one by one. So the area of the base here, again, is the 36 square centimeters. The height of the figure is 15, and the volume of the figure is the 12 times the 3 times 15, or 36 times 15, which is 540. Okay, our last one, the area of the base, again, 12 times 3 centimeters squared, 36. And the height of the figure now is x. So we have a variable height for this figure, x centimeters. And we're asked to write and describe a function that will allow you to determine the volume of any rectangular prism that has a base area of 36 square centimeters. Okay, so hopefully you've thought about that, but look back on the exercises that we have just done. We've taken and we've multiplied that base area by the height. Here's the base area, 12 times 3. There's the height. Same thing that we did over here, only I can't find it. Let's see, there it is. Yeah, we'll just go here. So the height of this figure here is x centimeters. And if we want to write the function, it's going to look like this. So the volume of that prism is 36 centimeters squared times the height, which is x centimeters. So that will give us that, that volume. All we have to do is input the height. All right, let's look back at our table right here. So the area of the base on all of those prisms was 36. What differed was the height. We had 3, 8, 15, and finally a height of x. So any height, any unknown height could be substituted in there. But we can see that each time we did this, we were essentially multiplying by the 36 first. So here's the 36 right here, and in this one, there's the 36 and 36. So we've been doing it every time. So we've now used functions to describe both the area of a figure and volume as well. All right, so let's just do a quick review. It says rules can be written to describe functions by observing patterns and then generalizing those patterns using symbolic notation. We did that twice in this lesson. We did it first with the sort of picture frame activity, and then we did it second with these different prisms that all had the same base area. Okay, so once again, we talked about these when we talked about volume, but volume always has to be greater than or equal to 0. Can't be negative, obviously. The volume of a unit cube is a rectangular prism whose edges are all a length of 1 unit. The volume of that unit cube is, by definition, 1 cubic unit. If two solids are identical, then their volumes are equal. Okay, that seems to make sense. And then if two solids have, at most, their boundaries in common, in other words, you can think of blocks backed up to each other, their total volume can be calculated by adding the individual volumes together. Those figures are sometimes referred to as composite solids. So it's a very natural thing to do to divide it up, so they're just telling you that you can. Okay, so that is lesson 9. Good luck with the problem set, and we will see you back here for lesson 10, or except those of you who will be there on Monday, and we'll do it then. Okay, have a good weekend, and good luck with this problem set.